Thanks again for coming for the third lecture. So today we will have about, I think, something like 50 or 60 minutes of lecture, and then the last 15 or 20 minutes I will kind of try to improvise, to play a bit with this code here with a live demo. Let's see how that works. So the code is already on the website, so you can download the full package under the lecture notes. And so this contains essentially everything. It contains the code, it contains the official documentation, it contains initial conditions, the Python scripts to do the analysis, and essentially everything. So the main challenge, and I can only give limited help for that, is actually to install the code on your machine, which requires these couple of libraries. I mean, it's all described in the documentation, but you need to install a bunch of libraries to make the code actually work. It's not a lot. As I mentioned the last time, it's MPI, HDF5, FFTW, and the GSL library. So it's actually only those four. And you should have some kind of compiler on the system, like a GCC or whatever you prefer. Yeah. So in principle, it shouldn't be hard to install, but it depends on your system and your configuration how hard this can be. If you have a Linux machine, it should be pretty straightforward. Yeah. Good. So before we come to this demonstration and playing a bit around with this, I briefly want to talk about simulations of dark matter models which go beyond CDM. So the last two lectures, we mainly talked about CDM simulations, and we also convinced ourselves, especially in the first lecture, that on large scales, lambda CDM is a very good theory. So it describes many properties of the clustering of galaxies and many other things incredibly well. And in fact, as you will see tomorrow, if you also include hydrodynamics, you can also not only describe the clustering of galaxies very well, but if you do hydrodynamics or semi-analytics, you can also explain a lot of the characteristic of galaxies in a statistically correct way compared to the observations. So this works all extremely well. So then the question actually is, why would you even bother going beyond CDM? And there are multiple reasons for that, and I cannot go in all the details here, and again, you might know this better than I do, but as you might know, the canonical WIMP has not yet been detected, and people have been looking for this since many decades now. So the parameter space gets smaller and smaller, and this whole basic idea of the WIMP miracle is also not so. This is not such a strong argument anymore because the parameter space shrunk so much already. So that's one reason to think about alternatives. Another reason is, and by the way, this also applies for the axion to some degree, because also none of the axion experiments, although they are far less, and the parameter space is far less explored, also there nothing was conclusively found yet. So that's one kind of motivation why you think beyond CDM. Another motivation is that if you look at galaxies not on the very large scales, but on smaller scales, and by smaller scales I mean, for example, the distribution and characteristics of satellite galaxies in the Milky Way, for example, or in the local group, then you try to, you kind of find in some areas, or if you look in some observations, some discrepancies between the theory and the observation. So some things that don't match perfectly. One example that we discussed before was the missing satellite problem. That is now kind of understood because it can be solved if you involve all the other physics, like the physics of supernova and reionization. But there are other problems where it's unclear whether they are solved at that point. And I cannot go in all detail of that, but I just want to give you a basic idea what one of these problems or two of these problems are, just to motivate this a bit further. And so over the last couple of years, one of the strongest problems that was pointed out was this so-called too big to fail problem that was pointed out by Mike Boyen-Kolchen. So this is a very busy slide, but essentially what you see here is, let's start with the data points here. So you see these data points are always the same in all these panels. So these are actually measurements of the so-called circular velocity of actual satellite galaxies of the Milky Way within a given radius. So you have the radius here, and then you have the so-called circular velocity, which is kind of a measure of the enclosed mass. And you can also translate this as enclosed mass. And you can put these data points based on observations. And so this is not such a trivial observation. It has to do with measuring the kinematics of stars and so on and so forth. So it's rather difficult. But if you believe these data points, then these are the values that you get in these 6 panels. In addition to these data points, what you also see is a bunch of lines here. And the reason why there are 6 panels is that the lines come actually from simulations, and they come from 6 different simulated halos, Milky Way-like halos. And what they show is actually the circular velocity profile of, for the thick ones at least, of the most massive subhalos in the simulation. So if you only look at the thick ones, these are the enclosed mass profile of the most massive subhalos in the simulation. And the problem is, this is what this too big to fail problem is about in easy terms, the problem is that these data points, which correspond to the brightest satellites in the Milky Way, don't agree essentially with these lines. So the lines are always above all the data points. And many sigma, you see that they are completely discrepant. So what this means is actually that if we take the brightest satellites of the Milky Way and measure their enclosed mass at a given radius, and then we take for a Milky Way halo, which has supposedly all the properties of what the Milky Way halo should look like from a simulation, and we compare then the circular velocity profiles, we get this significant disagreement. So this is different from the missing satellite problem. This is more structural problem, because it tells you that in these simulations, it seems that the halos are too dense. So within a given radius, they have too much mass, because that is what brings up these curves. So if you would reduce the mass from these halos or subhalos, you would bring down the curves, and you would get better agreement with the data. So this is this too big to fail problem, and you can see this is present in all these 6 different realizations. And people have simulated this also for other systems or in many more systems. I mean, this is now quite old paper, but it is present in many of these simulations. Now, one caveat of this simulation is that this simulation only includes dark matter. It still doesn't include all the baryonic physics, so the hydrodynamics and all these things. Also no supernova feedback. And there are some simulations that repeated this exercise with supernova feedback. And what then happens is, at least in some of these simulations, not in all of them, but in some, that you can actually remove dark matter from the center of the dark matter halos and create, reduce the density in the center, and through that process, you can then also get better agreement here. So it's possible that the disagreement here is only due to the fact that we don't model the supernova feedback and all the other processes that we know happen in galaxies for this comparison. But again, this issue is not yet fully settled. There's no full agreement even today that is the full solution, but that is one possible solution. There's in the observations there's less matter. So we have in the theory predictions too much matter at the centers of dark matter halos.
So then what my instinct says is that the colder you go, the more clumpy dark matter.
Yes. Mm-hmm.
So wouldn't that mean that this is the
No, because actually it's quite the opposite. So people have tried to solve that by making it warmer, because if you have warm dark matter, for example, you can create slight cores, small cores at least, in dark matter subhalos, and that brings down these curves. So there, a couple of years ago, a couple of groups have tried to solve this problem with warm dark matter. This doesn't work so well with the current mass constraints on warm dark matter, but that's one idea how to solve that, right? So there are essentially 3 ideas how to solve it, or 3 main ideas. It's the baryonic physics through the supernova feedback. It's warm dark matter, and it's another thing that I will talk more about this later, which is actually self-interacting dark matter. So this is one specific problem, and which kind of motivates looking beyond CDM. And again, as I just mentioned, there are many alternatives, popular alternatives at the moment. There's warm dark matter, which, yeah, you have a question? For these numbers, where we have rough estimates with an effect of 2 of the Milky Way mass, and these halos are all kind of picked to be in this rough mass range of the Milky Way mass. Yeah, so this is essentially the virial mass of the virial mass of the parent halo. Yeah, so these are curves for the individual subhalos within this main halo, but this is the mass of the main halo. And these masses, I mean, you have to take those close to what the Milky Way mass actually is. Otherwise, the subhalo population and everything will change. If you take here a 10 to the 14 cluster, these profiles will look very different, and there's no point in comparing this then to the Milky Way measurements. So you have to pick a halo which is representative of the halo of the Milky Way. Yeah. Okay, so there are, as I said, a couple of alternatives. Warm dark matter has always been kind of popular, but it has pretty tight constraints now on the mass. Then self-interacting dark matter became more popular over the last couple of years. And very recently, there's this BCDM, or also fuzzy dark matter, which was discussed in a paper, I think a year ago, by Scott Romain, Ed Witten, and various other people who argue that actually the dark matter is not a neutralino or WIMP or anything like that, but it's rather an ultralight axion, a very light axion, such that that you can actually get quantum effects that are so large that the de Broglie wavelength is of the order of a kiloparsec. And then if you have a de Broglie wavelength which is of the order of a kiloparsec, then you create cores at the centers of halos just because of the Heisenberg uncertainty principle, because you cannot put more dark matter in the system at the center. So this is a pretty recent development, and a couple of groups have started simulating this to look in structure formation in these models, but this is not yet very well explored, at least numerically at that point. Okay, and of course there's many other models that I probably don't know about, but these are three leading candidates, I would say, that people have explored a lot over the last couple of years. This is, for example, a figure from Mark Lovell from a paper also a couple of years ago, where he simulated this halo that I showed on Monday, this Aquarius halo, which is the CDM prediction here. He simulated this in warm dark matter. And in warm dark matter, you see that this halo looks like this. So you can see that this looks distinctly different. The strongest effect you see is actually this significant reduction in the abundance of the subhalo, which is simply due to the cutoff that you get in the initial power spectrum in warm dark matter, because the particles are faster, so you cannot collapse on so small scales. So you get a cutoff, and then you don't form halos on the very small scales. So that is the most obvious difference. Yeah, but of course the main features of the main halo are kind of unaffected, but the subhalo population is significantly affected. So I want to talk more about self-interacting dark matter, because this is something that I and also Tracy have worked a bit on over the last couple of years. So we just want to focus a bit on that. And so I want to start with this slide here, which actually gives you an idea how self-interacting dark matter works, just qualitatively in terms of how it affects the halo. So what you see here in these four pictures is the same halo simulated in different models. So here it's simulated in CDM, and here are three different SIDM models. So these are different models in terms of their parameters and how the cross-section is parameterized. So the basic idea of SIDM is that the particles are not collisionless anymore, but they can interact with each other with a certain cross-section. So this whole idea that we had yesterday of avoiding scatterings, you do the opposite now, because you say there is some interaction going on between the dark matter particles. Yeah? And this interaction, whatever that is and however that works, it doesn't matter for these simulations. This leads to scattering. And then you can see, for example, in this model, that the impact of SIDM compared to CDM is that you get a significantly rounder halo. And I come to the reason for that in a few minutes. And you can also see, at least for that model, that you get a bit of suppression in substructure. It's not nearly as strong as in warm dark matter, but you get a bit of that. And these other two models are also SIDM models, but they are still within observational bounds. So this is essentially ruled out, this model. It's just the extreme case to show you what it does. They are still allowed. And I will mainly talk, well, if I make comparisons to observations, I will mainly talk about these two models here. Okay, so what is the main thing that happens beyond making the halo rounder and so on? Is actually that the density profile changes significantly. So this is the density profile that we looked at already on Monday, where we saw this NFW profile. So this is the black curve, the CDM prediction of the density profile of the main halo. And you can see this is again this -3 slope and the -1 slope in the center. So this is a typical NFW profile. But then you can turn on, and this is shown in the blue, green, and red lines, you can turn on these self-interactions. And what you can see is, indeed, you get this suppression of density. because what's happening is that you essentially, you have the particles interacting, and you have essentially a transport out of particles from the center to the outer part because of these interactions, and that removes the mass here. And that's very good, because that is what we want to solve this too big to fail problem, because we said before we have too much mass in the predictions compared to the observations at the centers. So this is actually exactly what we want, so it goes in the right direction. And by the way, this is also one of the main reasons why SIDM was revived again, because it has this feature and it has implications for the too big to fail problem. So you realize that this paper was actually written also in 2012, which is more or less the same year where the too big to fail problem was pointed out. Because before that, SIDM was kind of dead for nearly 10 years. So does anybody know who first pointed out SIDM in the astrophysical context? It was a pretty seminal paper around 2000. I mean, they were not the first to talk about self-interacting dark matter, but in the context of astrophysical problems and how they could relate to that. This was actually pointed out by David Spergel and Paul Steinhardt around 2000. So that was in the context of the missing satellite problem mainly. So there, if you have, as you saw before, if you have large cross-section, you can suppress the abundance. And the idea was, well, maybe self-interacting dark matter is required to solve the missing satellite problem, or that was at least one of the ideas in this paper. However, then 1 or 2 years later, people have looked at various observational constraints, especially from cluster observations, and they could constrain the cross-section. The cross-section they came up with was so small that any effect on the subhalo population was negligible. And if you look at all SIDM papers over the last 20 years, you will actually see that after 2002 or 2003, the number of papers literally dropped to 0, and 2012 or 11, it just went up again. So because initially it was sought to solve the missing satellite problem, but then it was ruled out, and then now we want to solve the too big to fail problem. Yeah. Okay. Yeah, this is an interesting plot which actually shows you, and I should have asked before I showed this plot, but maybe, which shows you the number of scatterings per particle. How often does a dark matter particle undergo a scattering actually to make this all work? So what this shows as a function of radius, the average number of scatterings at a given location. And you can see for these models that are not yet ruled out, to see an effect or to do something with self-interacting dark matter is actually sufficient if you have 1 or 2 scatterings over a Hubble time. So in 10 gigayears, it would literally only scatter once or twice, and that's sufficient to have an effect on the halo structure. So you don't need an enormous scattering rate. It's actually sufficient to have these 1 or 2 scatterings, as I will show in a few seconds. Yeah, and again, this model, which has 20 or so, this is, again, ruled out. Okay, so then we want to solve the too big to fail problem. So how do we do this? Well, we look at not at the main halo now, at the density profile, but the density profile of the subhalos. So we plot the density profiles of many subhalos. So we pick, I think, the 10 most massive subhalos here in the different models. And you can see the black is again the CDM prediction. And you see that they all peak towards the center. They have this cuspy behavior, again, typical NFW-like. But then for the models that have self-inductions, you see this reduction. Yeah? You see this significant reduction here in the density, and this is a logarithmic scale, so it's really quite strong from the black to the blue, for example, or to the green. And that's again an effect of the self-inductions. Now, if you take these density profiles and then plot circular velocity profiles, similar to what I showed you before, so these are the same similar panels as what I showed at the beginning. Again, they are the data points from the Milky Way. And then there's the CDM prediction, and here's the too big to fail problem again. All the lines are above the data points. But then I turn on the SIDM. And you see for all these models, it pushes the theory predictions significantly closer to the data. It's not a perfect agreement, but it goes in the right direction. And that was kind of the main reason why, or it's kind of the main reason why people think again that SIDM is an interesting candidate, because you get better agreement with the data. When we did that work, we didn't tune for anything. This was just, we picked a few models, and this was just a natural outcome of the model. So you could probably do better if you picked the model a bit carefully. But the basic motivation why SIDM became more interesting again is because you got closer to the data if you turn on self-interactions in the dark sector. Yeah. And you can clearly see this difference here between the black and these allowed models, the blue and the green. Yep. Well, yeah, that's true. I mean, there are still various issues with it. I should, however, say that each of these data points is just one satellite measured. So it's not exploring the curve, the full curve of a satellite, because you can only measure this reliably at essentially one. This has to do with how the observations and the analysis is done. You can only reliably measure this, or reasonably reliably measure this at one radius. So each satellite has one point here. Of course, you know, if we could map out this profile for this satellite, for example, so I'm not sure how it would look like, but it would have a similar shape like that. But we cannot, you know, you cannot see it because we have it only at one point measured always.
I just can't envision any particular thing on just like taking a half the screen that would agree with all of them. Like, so you're always going to have some that are going to disagree rather remarkably with anything. Any shape can happen.
Yeah, I mean, I agree. I mean, I don't claim that this is a full solution. It's just hinting towards some physics that brings the data in better agreement with the theory. That's the only point. Okay, good. So then you can also summarize this. So this is kind of a summary of all these results. So it's again the same data points as before. And now there are a bunch of, you know, these are all, except for the black line, these are all different SIDM models. And you can see for all these models, these are different parameterizations of the cross-section. You always get closer to the data. In some cases it's better, in some cases it's worse. And if you are interested in the cross-section, so these are the typical cross-sections here. So there's a distinction in the theory between models that have a constant cross-section and these velocity-dependent cross-sections. And so the blue and the green are these velocity-dependent cross-sections, which have the advantage that at high relative velocities, you know, this is always the relative velocity between the particles. At high relative velocities, you see that the cross-section is extremely small. That means on cluster scales where we have some constraints on the self-conducting dark matter, on the cross-section, you can easily circumvent all these constraints because the cross-section is just tiny. Yeah, so you see it's extremely small. Whereas with a constant cross-section, you have essentially, well, current constraints say that it's very difficult to have something larger than 1. If you really believe in a constant cross-section. Yeah, so you cannot, if you look at the literature and the estimates and constraints people derived, it's just difficult to get to values larger than 1 without violating the constraints. However, with a velocity-dependent model, you can have extremely large cross-sections here on the small scales where we have no constraints and still obeying all the constraints, essentially. Yeah. And I'm not a particle physicist, but from a particle physics point of view, and again, you might know this better, this shape of the cross-section, you know, this is a v to the minus 4, is much more natural to come out from many alternative dark matter models. So this is having this constant cross-section is less natural also to some degree. Okay. Now, if you have the self-inductions, and you know, if you believe that that's the case, that dark matter is self-inducting, then you can also look at the phase-space structure again. And this is just from another paper where we have the CDM phase-space structure, and then we have a bunch of self-inducting models again. And you can see that most of them look actually pretty similar to the CDM case, except for this SIDM10. This is again this extreme model with this very large cross-section. And again, you erase a lot of the substructure there. Yeah, all these points here are actually substructure in this velocity position space. And you erase a lot of stuff here, which is mainly because of the large cross-section. Yeah, but again, just let me remind you that that model is ruled out. It's just shown as an extreme case. So for most of the other models, you see some differences, but clearly the number of substructure is not strongly affected in those cases. Another interesting thing is if you look at the velocity distribution of dark matter near the sun, and you remember on Monday we discussed this also briefly, where we said it's not Maxwellian, because you have the significant deviations from the Maxwellian distribution. So this is shown here on the left again. So you have the black dashed, which is the Maxwellian, and then the black solid is the CDM prediction for 3 different radii. You know, this is actually the solar position, and this is further in, indicated by these radii here. And it kind of confirms what we saw on Monday. So the dashed line in all these cases doesn't agree very well with a black solid line, which simply states again that the halo is not fully relaxed and you have significant deviations from the Maxwellian. However, if you turn on a lot of self-inductions, then the system, because of this collisionless character, will get quicker to equilibrium. Yeah, so, and especially for this red model, which is again the extreme model, you see that actually for all these cases, the red line, the red solid line, traces the black dashed line very well, which is simply because you have so many collisions that the system is driven very quickly to equilibrium, and it really then follows very closely the Maxwellian distribution. And all the other lines are kind of intermediate cases. Yeah? So you see actually that the allowed models are, for most of the cases, pretty close to the CDM case. So in general, the velocity distribution doesn't change too significantly for the allowed models. Okay, good. So that's the basic idea of self-conducting dark matter, where the main difference between CDM and self-conducting dark matter is that you have a finite cross-section for interaction. So you give up the collisionless character. Yeah? So it's different, for example, from warm dark matter. In warm dark matter, you give up the cold character. CDM is characterized by two features. It's cold and collisionless. In warm dark matter, we give up on the fact that it's perfectly cold. In SIDM, we give up on the fact that it's collisionless. Does everybody see what I mean? Now the question is, and this is something that I want to talk a bit more about now, is what if you do actually both things at the same time? Yeah, so what happens if you have a model, and again, I'm not a model builder, I just take some model that somebody has developed. If you have a model that has a modification to the initial power spectrum and has self-interactions on top of that. Yeah. So this is pretty natural because many of the self-consistent, self-interacting models also have some significant deviations in the initial power spectrum, so they don't follow exactly the CDM initial power spectrum. And this is something that Francis-Jan Surasin and Jesus Zavala and Thorsten Bringmann and many others have worked on, and we've put out a couple of papers 2 or 3 years ago. And the basic idea here is the following, that you have now two ingredients, as I said. You have initial power spectrum, which looks very different from the CDM case. So this is shown here. So this is as a function of K and as dimensionless power, the linear power spectrum. In black is the CDM line. And then in the black dash, these are just some warm dark matter models. This is a typical warm dark matter cutoff for different masses here for the warm dark matter particle. And then you see these colored lines, which look very strange. So these are from these ethos frameworks. So this ethos framework is essentially an effective theory that where you can take, not arbitrary, but a large range of dark matter models and map it into an effective theory, which just describes the initial power spectrum and the effective cross-section. And these colored lines were taken from some of these ethos models. And what you see here, they have a similar general behavior as a warm dark matter model, but then on top of that, you have these kind of oscillations. Yeah. Yeah, this is just different models. So the model has some free parameters, and it's described a bit more in these two papers, but it's essentially different parameters picked in the parameter space. And they were picked essentially in terms of how strong the cutoff here is and how large the cross sections can be to span a certain range. Yeah. So again, the difference here between the warm dark matter and these models is you see these oscillations, and they are a bit. If you look at them, it looks a bit like baryonic acoustic oscillations. And in fact, this is something which is known, and again, maybe many of you know this, as dark acoustic oscillations. So these are interactions of the dark matter with some relativistic species at very early time, which leads to a relativistic plasma, where also then you get these oscillations in this dark matter fluid, essentially coupled to the relativistic particle. And then you get these oscillations. Again, I'm not an expert in the particle physics theory, but that is essentially what comes out of these models. So if you want to know more about the actual particle physics, you should look at that paper. So that's the initial power spectrum that we plug in, and these are the cross-sections. Again, these are all velocity-dependent cross-sections because that's now done within a self-consistent particle model within this ethos framework. So you don't get constant values, but you always get these velocity-dependent models. Now you take both of these things, and simulate this and look how the halos actually look like, or how structure formation looks like. And to give you a first idea, let's look first at this one. So you first look essentially at, you can simulate a large volume and look, for example, at the halo mass function. Again, this is something we discussed on Monday. So the halo mass function tells you, for a given halo mass, how many halos there are, the number density. And this is shown here again. In black is now the CDM prediction again, and then in colored lines are all the different ethos models. What you can see here is this suppression towards smaller scales. So that's very similar to warm dark matter, where you also get a suppression on smaller scales, which is simply because of this suppression in power, right? You don't have power on these scales, so there's a lot of power still in CDM, which clusters on much, much smaller scales, as we heard the neutralino down to the Earth mass. But that's not happening here because you cut off the power spectrum because of this coupling with this relativistic species here. So that causes essentially this drop. And you can also see this a bit in the nonlinear power spectrum. So you can run your simulation and calculate the nonlinear matter power spectrum at all times. So at redshift 10, 6, 4, 2, and 0 here. You can see that also there, especially at early times, you see this difference in the power towards smaller scales. So that's something that's different from SIDM, because none of this happens really in SIDM, but it happens in warm dark matter. So it's kind of a similar behavior to warm dark matter. And the reason for that is because it has the same or similar cutoff, essentially, in the power spectrum. Now, if you, excuse me, so if you then run the simulations and look at individual halos, so this is these are 4 different simulations in CDM, Ethos 1, Ethos 2, and 4. Yeah, there's a reason why 3 was dropped. So, so you see in CDM, there's an enormous amount of substructure again, and much less substructure in the other models. Again, this is because of the cutoff. It's not because the cross sections here are so large, because they are rather reasonable here. So they are also allowed and not ruled out. But it's, let me play this again. It's really because you have the initial power spectrum modified in these models. Again, it's similar to warm dark matter, if you remember the slide I showed towards the beginning of the lecture. Yeah.
Do you remember what each of these were, or not? Ethos 1, is it just some scalar, or?
No, they are all the same. They are all the same particle physics model. It's really all the same. Like, it's a dark matter particle at early times coupling to some relativistic fermion. The only difference is actually what you choose for the masses of the gauge boson and the coupling constants. It's the same particle physics model, just different parameters that you choose. Yeah. And again, it was mainly done to explore here a certain range in the cross sections and in the cutoff. Okay, good. So this is how a Milky Way halo looks like. And then you can look again at this too big to fail problem. So this is shown here. It's again circular velocity as a function of radius. Again, the usual data points that we showed before. Black is again CDM. And then you get this huge range here of values which come from all these different Ethos 1, 2, and 3, and 4 models. And 4 is kind of a model that we, where we have chosen some parameters which kind of work reasonably well with most of the data points, which is shown here in yellow. Of course, these are still not included, so not everything is perfect, but you can see it goes through a reasonably large amount of data points now. So, and in fact, it seems like if you really want to, solve this problem, and maybe also other related small-scale problems, it's actually a very good idea to have a modification of the initial power spectrum to some degree, plus self-inductions, because the combined effect leads to a better agreement here. On the left, what you see here is not about the structure or the circular velocity profile of the subhalos. It's more the sheer abundance of the subhalos. So this shows as a function or the number of subhalos with a given Vmax, or above a given Vmax, it's greater Vmax. And Vmax is the maximum circular velocity. That's also kind of a measure of the mass. Yeah. You can just translate this as a mass measurement. And then you can see these black and the black dashed line. These are Milky Way measurements, so what we know about the Milky Way. The black solid line here is the CDM prediction, and then you get all these different ethos models, and you can again see that you get actually better agreement with the data if you turn on these ethos models. Yeah? And this is a pure effect of the change in the initial power spectrum. Yeah, so with self-inductions alone, you would not get this. You have to combine essentially both to get this plus this. However, as we said yesterday, the missing satellite problem is anyways not a big problem, so it's most likely that even with these green and yellow models you would get along, because if you turn on baryonic physics, then you would also get probably close to this dashed line here. Okay, so we're nearly done with this. So what's shown here is again the same plots that I showed before. So circular velocity profiles again and abundance, but now disentangling the effect of self-inductions versus the power modification. Yeah, you see here for 3 different ethos models, 1, 2, and 3, the CDM prediction in gray always, and then in black the full model, and then in red and in blue you see essentially a subset or the subset of the model where we only have the power spectrum modification or the SIDM modification. And what you can see here is very clearly that if you have, for example, only the power spectrum modification and compare this to the black, which is the full model, you see that the power spectrum modification clearly does all the effect for the substructure abundance. On the other hand, for the reduction here in the circular velocities, SIDM plays a crucial role. So this is what I mentioned before, that you need essentially both to get a reduction here and a reduction there. Yeah? So it's the initial power spectrum plus the SIDM modification. Okay, then just a quick comment. I mean, you saw this plot before where we looked at the faint and or the low mass halos, which is severely suppressed. So the question is then always, are there any high redshift constraints that could rule out these models? And the most prominent one is something we are currently working on, which are Lyme alpha forest constraints to constrain the power spectrum cutoff. Another thing you can do, which we have done before, is looking at the optical depth that is constrained pretty well by Planck, which is this blue band here. And then you can see these different lines here. I mean, there's some uncertainty here, but the bottom line is that despite the fact that you have this severe suppression here in most of the models, they are all still kind of compatible with the optical depth with respect to Thomson scattering. Yeah, so there's no violation in the high redshift universe of these models. So this still has to be verified with Lyme alpha forest constraints, but at least that test can be passed by these models. Okay, so now before I come to the next subject, let me briefly talk about another issue, another problem beyond the missing satellite and the too big to fail. So 2015, Oman et al. Pointed out a new problem, which is now known as the diversity problem. So what they actually did is, this is summarized in this plot, and I will only, again, scratch the surface here, but if you look at these two plots, what they actually show is, as a function of Vmax, which is again a proxy of the mass, the circular velocity measured at a certain radius. And they show this here for observations in blue, all kind of observations, so you see the references there. And they show it for some simulations. And by now this has been extended a lot more, so people have simulated more systems and looked at this more in detail. And the basic problem is that this range of values at a given Vmax, this range of Vcirc values that you see here, is never reflected in any of the theory models that we have these days. So essentially we have too little diversity at a given Vmax. So the halos or the satellites or the dwarf galaxies that we have, they look all too similar to some degree compared to what nature actually produces. So nature produces a significant variety here. I mean, it's a bit hard to tell from this early paper, but as I said, there were other papers looking more detailed in that. And this variety is not seen in the theory. So that's known, that's the very latest problem, which is kind of the diversity problem. Has anybody heard about this before? Okay. So who heard about the too big to fail before? Ah, so very good. So that made it into the particle physics community. So this is another big problem. The problem with the diversity problem is that you can really only talk about this if you do hydrodynamic simulations, because all these points are essentially hydrodynamic models. So and the problem there is, as you will see tomorrow, there's a huge range of uncertainties how you model the hydrodynamics and the star formation and everything. So it's not as clear cut as the too big to fail, but it is a severe problem. And this is a sentence that I took from the paper, where they would also argue that 7 dark matter would be an interesting case here to solve this. And in fact, there was some work by a postdoc at Riverside, who together with Laura Sales, who's a faculty in Riverside, looked at this in SIDM models. And again, this is a very busy plot, but the main point is here that all the squares are CDM models and all the triangles here are SIDM models. It's the same plot. It's again Vmax versus Vcirc. And without doing any statistical analysis now, but if you look at it, there is a bit more diversity in the SIDM model. Yes, you span a larger range essentially with these triangles compared to the squares. Yeah, and the reason is that, well, as it is written here, it's a combination of baryonic effects, so there's also some baryonic modeling here, and the SIDM and the core formation that leads at the end of the day through the formation history or through the formation of these halos to this larger diversity. So, this was pretty recent. This is still not all fully explored, and this is a simple toy calculation, but it might be that if you have SIDM combined with baryonic physics, that you really get this larger spread and that you get closer to the solution to this diversity problem. Yeah. Okay, good. So then, for the next 5 minutes, before we slowly get to the hands-on session, I want to talk about something that I worked on with Tracy over the last year, which is actually inelastic self-inducting dark matter. So all the SIDM simulations I showed so far were so-called elastic models. That means that the scattering happens like between 2 billiard balls, so there's perfect energy conservation. And as you might know, that might not be the most natural model. For example, if you have a 2-state dark matter particle with a ground state and an excited state, you could have exo and endothermic reactions during the actual scattering process. So Tracy and Kathleen Schutz worked on a model a couple of years ago, which you can analytically write down for a simple 2-state dark matter model, and we have implemented this in some of the simulation codes to actually see what's happened. So I will only spend a few minutes on that, but I just, and this paper is not yet accepted, it's still in the refereeing process, but I just want to show you how this looks like if you go beyond this elastic case, because there's very little work done on inelastic models. Actually, this is one of the 2 or 3 papers that actually did this, so it's not yet very well explored. So this is the outcome of one of these simulations. Again, we always compare to CDM. So this is the inelastic case. This X, or this init here, this means how many of the particles are initially in the excited state. This is a free parameter of the model. So to maximize the effect, we put here 100% of the particles at early times at redshift 130 or so in the excited state, and then start the simulation from there. And what you can see is, if you look at that, then this looks kind of like a fuzzy version of the CDM case. Yeah. So you see that the central density is lower in the main halo and also in the subhalos. And that actually is true for all the subhalos here. Yeah, it's like a smoothed or fuzzy version of the CDM case. And the reason for that is that if the particles, or it has 2 reasons. One reason is that in SIDM in general, you move particles out from the center already in the elastic case. But in these inelastic models, you get even a stronger effect because the way this model was constructed is a pure exothermic reactions always. So the 2 particles collide at the center of a halo, and then a lot of energy is injected because they decay from the excited state to the ground state, and then you can actually unbind particles from the center. So you can actually literally remove particles with very high velocities outside of the centers, and this is what leads to this significant density reduction here. You can also see this if you split the density of the particles in, this is a bit of a confusing plot, so if you only look at these 6 panels here for the moment, forget those panels. So what this shows is the total dark matter density for an elastic model, and the total dark matter density for the inelastic model. So there's no CDM here, it's only the elastic case and the inelastic case with the same setup for the cross sections. And then what you see here is, for the inelastic case, how many ground state particles you have and how many particles you have in the excited state. And so you see, despite the fact that a lot of particles decay, you don't find many of them in the center, so this is nearly black here, because they are all immediately removed from the center because of the energy that is injected due to these exothermic reactions. And what you see here in the other 6 panels is essentially a case where not 100% and the excited state initially, but only 50%. Then the effect, as you can see here, is less extreme, but the physics is still the same, so you can still eject particles. So why is that interesting? Well, because you can then create larger cores for the same cross-section, essentially. So you can circumvent some cross-section boundaries or constraints, and this is shown here. Again, this is a density profile. It's a bit busy, but if you only look here at the thick solid lines, so the black is again CDM, and then blue and red are SIDM models, where the blue is the elastic model, and the red is an inelastic model with the same cross-section setup. And you can see you get a stronger reduction of the density in the center with the inelastic model, which is simply because of this energy injection if the particles decay. And so that means for the same cross-section, you get lower density, So you can circumvent some of the cross-section constraints. And that's the main reason why we looked at those models. And then you can look at the satellites again. So these are density profiles of the satellites, of some satellites. You can see the same effect here. The density goes down if you have an inelastic model. This is for the case where you have only 50%, you still get an effect here. It's smaller than the case where you have 100% excited, but it's still visible. Yeah, so that's the main reason why we looked into these things. Okay, good. So that's nearly it for today. I just want to make one comment about this scalar field dark matter. Do you have a question? Yeah. Yes. Okay. Yeah. So so technically, you can do many things very similar. So first of all, there are different ways of doing it, but most people do it in the following way. You use the same infrastructure that you have for the CDM simulations, and then the only difference that you have is that for each time step where you evolve the simulation, you have your particle, your dark matter particle, and you make a neighbor search around that particle, and you evaluate the local dark matter density and the local velocity dispersion of the dark matter. So you have velocity information, relative velocity information, and density information. So that gives you a scatter probability for a given cross-section. And then you draw a random number. You probabilistically sample whether this particle should scatter with one of its neighbors or not. And if it scatters, you just exchange momentum between the two particles, essentially. The rest of the infrastructure of the simulation code stays exactly the same. The force calculation and everything else. You only have to do additional neighbor searches to identify potential scatters in the simulation. Yeah, they are very, you have, there's no, yes. Well, that's a point of debate whether this approach that I just described is really accurate. So, so I know that Jesus and his group are working on some better algorithm to develop, especially look into that point, whether this is really fully accurate or not. I don't know the result yet, but it seems for a large range of densities and velocities, it is kind of accurate, but there might be regimes in the simulation where this approach that I just described is not perfectly accurate. But in general, it's a pretty good approximation. Yeah. Yep. Uh-huh. No, it's not so much computation time anymore. I think it's really more like, well, to some degree it's always computation time, but these days it's really how you develop these sub-resolution models, so how you really do supernova feedback in the simulation, because, or for that sake, even star formation. Like, even in these simulations that mimic only a single Milky Way with gas, for example, you will have a mass resolution in the gas or in the stars of the order of 10 to the 3 or 10 to the 4 for the, or maybe 10 to the 2 for the best simulations. But that's not even close to what a real star is, right? It's still far away from solar mass. So you have to incorporate this in a kind of a sub-resolution model, and there's still some uncertainty there. However, there are a lot of groups now who are very successful in reproducing Milky Way galaxies which look perfectly realistic in all aspects you can think of, in terms of the, colors, in terms of the circular velocity profiles, in terms of the bulge to disk ratios, in terms of the masses. So there has been a huge progress, but there's still some uncertainty in the modeling, actually. Yep.
So earlier when we were talking about sometimes the only like 1 or 2 scattering events in the Hubble
Yeah.
would suffice. When working on the assumption, when people talk about collisionless dark matter, this was a bit of a simplifying assumption that, like neutrinos, generally speaking, can be, for most purposes, you can approximate them as collisionless. It's like approximating them as massless.
Mm-hmm.
They're not actually, but for most intents and purposes, they are. This sounds like general dark matter thing is actually physically there is no scattering off of each other, and that seems to me a slightly odd thing. Is that actually a physically motivated thing, or is this just a spherical travel taken to the limit?
Yeah, actually, I'm actually not 100% sure about this question. Maybe somebody else can answer that. I mean, if you have a real dark matter particle like a WIMP, what is the chances over 10 gigayears that it really interacts with another particle? So with another dark matter particle, I would think it's extremely, extremely low. So it must be lower than these 2 or 3 scatterings that we have in these models. It must be, because otherwise we would see an effect, right? If it would have, for example, 10 scatterings already, we would see a significant effect in the structures. So I don't know the number, but it must be very low. So maybe somebody else knows the number. Maybe that's a good exercise to figure that out.
Fundamentally, they're incapable of scattering. It's just, even with the non-self-interacting dark matter, it's just
Yeah, but I mean, you know the cross-sections on the cross-section limits on WIMPs, right? You can take that and figure out, even doing it with linear theory, what would be the probability of scattering over Hubble time. I believe it must be extremely, extremely low. So, yeah, so somebody might be able to calculate this. But okay, any other questions? Okay, so then last 5 minutes, let me just briefly talk about this subject. And again, I'm not an expert here, but I just want to highlight some result of a postdoc in Princeton who has been working on this also partially with me. So this is about this scalar field dark matter, which is also called fuzzy dark matter, ultralight axion dark matter, or BCDM. So this has a lot of names, but it's to some degree it's always the same basic idea that you have a very light particle, a very light axion, and by very light it's something like 10 to the minus 20, 10 to the minus 21 electron volts. So it's really very low mass, where the whole system behaves such that the quantum nature becomes very important. It behaves like a Bose-Einstein condensate, effectively. So then, if you are in that regime, then the simulations have to be done in a completely different way. So then, so somebody just asked this question, whether, you asked this question of that SIDM, how we do this. So that still works pretty much the same as CDM simulations, but these simulations work completely differently. So the reason why they work differently is, so this is just an example of some of these simulations. So what you, and then I come back to the difference. What you see here is actually you have this is an idealized simulation, not cosmological. You have a bunch of halos, which are modeled as spherically symmetric density profiles, and you let them merge together and then realize. And this is what you get as a function of time for the realization process. Yeah? And what's plotted here is essentially kind of the modulus or the wave function essentially of the quantum system, yeah. And what you get here then is, and that's why people are interested in it. So if you look at this merging process, you always get, these are the density profiles, you always get a chord-like behavior, which comes from the de Broglie wavelength, which is very large in these systems. You get cores essentially at the centers. And this is why people care about it, because we have all these core-related problems on the small scales. So people thought, well, maybe that's a good idea to look also into these systems where you naturally produce a core because of the Heisenberg uncertainty principle. Now, if you want to simulate those, as I said, you cannot use these CDM simulation techniques anymore. You have to do something different because you have to solve the Schrödinger equation coupled to the Poisson equation here. And that's very difficult, it's just very different from what you typically do in these n-body simulations. So there are so-called spectral methods and other schemes to solve this. And in fact, a spectral method was used here for that. And they are very accurate here, but it's a completely different approach. So if you're interested in the actual implementation, how this works, you should look at this paper where this is described a bit more in detail. You can then also look on larger scales. So this is a first cosmological simulation, which is also the first attempt, essentially. So you see here how this looks like on large scale, and you can see already that it looks rather different from CDM because the filamentary structure is much less pronounced here. It looks much more like a warm dark matter model. This was also more of an extreme case for the fuzzy dark matter, but it leads to visible differences essentially in structure formation. So people have only recently started simulating this, and not much is known about it, but it's an interesting idea that some people are studying these days. I mean, again, I'm not an expert, but it is an interesting idea. Yeah.
Do you know how does the potential look like for these scalars, for these ultralight things? Is it just mass, or is it like self-interactions?
It has also some self-interactions involved. So, but I'm not sure how it exactly looks like. So, yeah, I can't say. But it has a self-interaction component included as well. Yeah. Okay, any other questions? Okay, good. Then I would suggest we briefly look at this hands-on session. So this is just kind of a preparation for Friday. So has everybody seen this file on the wiki that you can download? Or is there anybody who has not seen this? So you should all download this on your machine because that contains everything. Yeah. So what you, let me just look at this here. So what you will actually download is this package. It's a tar.gz file. And if you unpack this, you will end up with a directory structure which looks like this. So there's a couple of files in here. Most importantly, there's a file called, or directory called ICs. And by the way, I will repeat this on Friday again. So it's just for those who want to get started early. So there's a directory called ICs. And there's a directory called code. And the main challenge, as I mentioned a few times, is actually to make the code compile. So the first thing you have to try is to go into this code directory, and then you see there's again a bunch of directories. You go into this gadget directory, so the code is actually called gadget. And what you see here is there's a documentation, and that also explains a bit how to install the code and what the code features are. And then there's a directory gadget2 which contains the actual code. You can ignore for the moment the other directories because we don't need those. So if you go to gadget2, you see a bunch of C files, so the whole code is actually written in C. And it contains also, as many codes, a makefile. Yeah. So the makefile has a bunch of options. This is all explained in the documentation. This is a very well-written PDF where all of this is explained. And what you can see here, and again, we will talk about this in much more detail on Friday, you can see already some options that might look familiar to you, or maybe not, but hopefully they do. There's this option PM grid, which is actually for the 3PM code, the grid size. How many grid cells you want per dimension. So here we want to have 128 grid cells per dimension, so 128 cube in total. Yeah. You also see our option periodic, which means we want to do the whole calculation periodically. Yeah, because we will do a cosmological simulation actually. Yeah. What else is there? Another thing you have to activate is this HDF5, because who knows HDF5? Yeah, this is pretty well known now. Nobody else knows HDF5. So what's the typical data format in particle physics? That's an interesting question actually. What is the data format for particle physics? Sorry? Okay, but in which, so, okay. Okay, good. So anyway, so HDF5 is HDF5 is a very well established industry standard, and it's just a lot of people use it, so it's very convenient. So I don't have too much experience with root, but it's just very nice, and a lot of libraries and bindings exist to all kind of programming languages. So you have to turn this on essentially, which also means you have to install the HDF5 library on your system. But they are part of any, if you have a Mac or a Linux, it's easy to install. Yeah, and these are actually all the options, right? So that you have to turn on, and then you just have to compile it. And it will compile if you have all the libraries installed. And to compile it, you just do as usual. Let's make this clean. You make a make, and it should run through. And at the end of the day, you get this executable here. Yeah, this gadget2 executable, standard executable. And I have copied this already before somewhere here. So it's also here in this root path. And then to start the simulation, and again, all this will be repeated on Friday, but to start the simulation, you just do, and it's also described in the user guide, which is part of that package. You just do a gadget2 parameter, and the parameter txt contains some setup values for the simulation. What is the starting redshift and so on and so forth, where are the initial conditions, and what is the softening value. It's all written in this param.txt file. And again, it's described in the documentation. And you cannot, I think you can actually run it like that, but if you want to run it faster, you want to use the MPI environment. So this, let me just check, this computer actually has 4 CPUs, so you want to make it faster, so you do MPI run NP4 for 4 processors, then get your 2 parameter, and hopefully it will now run. Yeah, so it will start, and you can see already that it goes through the different time steps. So these are, you see the time steps here always listed, and also some comments which should look familiar to you. There's a tree construction, which is for the gravity force. There's a domain decomposition and a Hilbert curve construction. So all these things that we actually discussed are going internally on. And you see also how the redshift is running, right? It starts at, I forgot where it starts, but it's now at redshift 81, and then it's at redshift 80 and 79, and so on and so forth. So it will eventually reach redshift 0. And at certain redshifts, it will make output in the HDF5 format. And this output can then be analyzed. The output contains, for all the dark matter particles in the simulation, so the simulation dark matter particles, it contains the position and the velocity and their masses. So you have all the phase space information of the dark matter written into this output file. Yeah. So this should run, I don't know, maybe half an hour or so. If you have a faster computer, it will be faster. Well, you get the idea. Yeah? So this is how you run it. And then, as I said, it will write the output somewhere. And specifically, it will write it in this output directory here. So if we go to this output directory, you see there are these files, snapshot 000, and then 001, 002. This is just as a function of time writing out the snapshot data. Yeah. And let me just see whether, HDF5 comes with this tool, HDF5 or H5 dump, which makes the ASCII output of the data. So you can look at that. So there's for example, these files contain a header which tells you the box size. So this is 50 megaparsec, so it's 50,000 kiloparsecs over H, essentially. So that's the volume that we simulate. Then there are some flags which we don't use. It also, let me see what else is there. It contains also the cosmological parameters. What is the omega 0 value? So this is a bit outdated, so it's 0.27. Then the omega lambda, the cosmological constant, is 0.73. The initial, or the redshift of that specific output is 90. So that's still at very early times. So this is all header information, which just describes the general features of the output. And then at some point you see all these numbers, and these are just the coordinates of the dark matter particles. Yeah. Of course, they are all stored binary. We just print this now here in ASCII, and you can see this is this HDF5 data type, which is F32. This is a float, 32-bit, in little endian encoding. And these are all the numbers that are stored. Yeah. So these are, you see there's a lot of numbers. And I cannot print all of them, but at some point then you will see the velocities. Just see. This is actually, yeah. So at some point you see the velocities. Yeah, so then you get the velocities, and they are encoded in kilometers per second. Yeah, so this first particle here has x velocity minus 240 kilometers per second, 74, 83. Again, float, 32-bit, little endian encoding. Yeah. Mm-hmm. Which scale? Sorry. Yeah. This is in this parameter file where you specify the system of units, essentially. Yeah. I come back to that in a few minutes. I will show briefly the parameter file. Okay, so that's in the output file. Of course, just with these sheer numbers, you cannot do much. So what is also in this package is a Python script. And I assume at least some of you are familiar with Python. So it's a very simple script, which is called plot map. So what this does is doing something very simple, namely taking all the dark matter particles, making a 2D histogram throughout the box, and showing a density field. So what you specify here is the snapshot number 6, which corresponds to a certain redshift. And then it calls the NumPy histogram function. Then it does some min-max clipping that I put in here, and then it just makes a figure. So it's the simplest thing you can actually do, just visualizing the data. So what you can then do, for example, you look at And I haven't yet run the simulation down to redshift 0, so whatever image we get will not look great now, because we just put redshift, or the number 6 here. So you call it with Python. Oh no, this is actually already redshift. Yeah, this is actually already redshift 0, so it prints out the redshift. But it's a very low resolution. So if I open the image now, don't get shocked. It will not look anything of the images that I showed to you before from the state-of-the-art simulations. So now is the moment of truth, because that is what you can do on your laptop. So it's called map006, so it's a PDF file. And this is how this super low resolution simulation looks like. Yeah. It's just very low resolution. So you see here, with a little bit of imagination, this is the cosmic web. Yeah, so this would be a halo. But you know, maybe if I have time, I create some higher initial conditions, because that was created for a summer school 2 years or 3 years ago, actually, where I always try to make it that it runs in an hour or so, but now the laptops are faster and so on. So, but these are the halos. This is the cosmic web. These are the voids. Yeah, so the color coding is just literally the density of the dark matter. And let me just make this a bit half size, maybe, so you get a better idea here, right? So this is in megaparsecs. So this is a 50 megaparsec box, 50 megaparsecs along X, 50 along Y, and then project through the whole box. It's not even a slice. It's a projection through the whole box. Yeah? And it looks like this. So this is what you should be able to do on Friday, actually, what we will try to do together.
Where is the center?
There is no center. It's a periodic box, right? So there is no specific center. I mean, the center of the simulation domain is here, right? But
They were not clumping to the center.
Sorry?
They were not clumping to the center.
No, they don't clump, because the force is periodic, right? So it's not that you have this cube and then turn on gravity and all collapses to the center. The whole gravity is done periodically, right? It's just a patch of the universe that we simulate. That is and our universe in that simulation is an infinite replicate of that box, because it's periodic. Yeah? It's similar to solid state simulations, right? If you have a piece of a solid, you periodically replicate this, and this is your whole material that you simulate.
On that note, if you look at the image, it looks like they put together. Is there a way to tile this so that you can see the way that the left side is?
Yeah, and I mean, it has to fit together, right? I mean, if you go from there, you have to end up there. Yeah, I mean, yeah, you can. Well, maybe some of you can try this. You can, you can tile it together, and then, yeah, it should match. Yeah. Yeah.
The resolution doesn't look like 128 times 128.
No, well, I have to check which particle number I used. So the 128 is also just the grid in the back, the particle mesh grid in the background, right? So the particle number, I have to check whether this is 64 cube. I would think it's 64 cube particles, or maybe even only 32 cube particles. So this 128 doesn't really, I mean, isn't exactly the particle number. It's just the resolution for the FFT in the background. Yeah. I have to check until Friday, or we can also check this now in a second, how many particles that actually contains. Yeah. Yep.
Okay, now I have a great question. How do you deal with Gauss's law with periodic boundary conditions? Think about it. Right? How can you have something that has a net mass and obey Gauss's law and have periodic boundary conditions?
Actually, I've never thought about that.
We have to do, for those of us who are in the business of doing QED, we have to worry about that.
Mhm. Yeah, I guess I would need to think about that, what the answer is. Yeah, that's a good question. I don't know. Okay, so just let me check 2 more things and then we are done. Because I want to figure out the particle number, because that question just came up. So the particle number should also be encoded in the snapshots. So we go to the snapshot. And then somewhere, here's the particle number. So this is 262,144. So what's 32 cube? Can anybody say what that is? Is that 32 cube? Sorry, what? Maybe it's even less than that.
32,768.
Okay, let me do this quickly. Let's stop here. Anyways, so that is the particle number, right? We can increase that and then the resolution would look better, but 64 cube. Okay, so that it's 64 cube particles. And then when I made the plot, then the grid, the bin size for the histogram was, let me just check. I used 32 bins, right, to avoid having too much noise in each bin. So I can increase this, for example, to 64. Let's make the plot like this. And then see how it looks like. Yeah. Yeah. So you can, for whatever reason, I picked 32 when I wrote this first. But yeah, you can, now it actually becomes more apparent that it's really cosmological simulation. So when you make the plot, actually, maybe change this to 64. Yeah. Let me just make this smaller. The softening, the epsilon, you mean? Yeah, let's have a look at this. So this is in this parameter file. So again, we will talk more about this on Friday, but the softening here is set here in units of kiloparsec, so that's 20 kiloparsec. Sorry? It's 50 megaparsec. Yeah, so you get clumping down on 20 kiloparsec scale in this 50 megaparsec, which is yeah. Yeah. Good. So that's the basic thing that we will try on Friday. So if you could download this and maybe until Friday try to install the code, that would be useful. The rest we can do here. Yeah, just running it and analyzing it and playing a bit more. Also, if you have ideas how to modify this Python script or whether you want to look. So for example, you could also, if you want to do something more challenging, you could also program your own cluster finding algorithm to find halos in the simulation, because these are collections of particles which are clustered together. A common approach to do this is with a friend algorithm. So you can implement this in Python. Then you can find a halo, you find the center of the halo, and you make a density profile, and you should get an FW profile. That's a bit more difficult, but I think there are even Python packages that do a friend-of-friend algorithm on the data. So, yeah. So you can essentially, everything that we discussed, or that I showed on Monday, you can in principle do with this simulation. Of course, not at that resolution level and so on and so forth, but the basic things work with this. And just to remind you that this simulation, the one that you see here, has already a higher resolution than the simulations in the 80s that ruled out the neutrino universe. Yeah. So it's already a pretty substantial resolution. And as I said, I might try to generate high resolution simulations if I find the time. So for example, a 128 cube. So today, just to give you an idea, so this is 64 cube. Today, what we can do on 50 megaparsec boxes is of the order of, if we really only do dark matter only, we can do 4,000 cube or so. Or even 5,000 cube. Yeah. It's really much larger what we can do. Okay. Any questions? Yeah.
Given the homogeneous isotropic conditions of the universe, square grid is not isotropic, and the axes.
Yeah, that's a good point. So there's a lot of concerns, and people have, again, tested this empirically a lot, whether the grid imposes some preferred directions in the calculation. And there's some rule of thumb what grid resolution you use compared to the particle number, which is, for example, why I used 128 grid cells for 64 cube particles, because this is essentially related to the Nyquist frequency of your sampling. So if you use very crazy numbers there for the grid, you can get some artifacts. Yeah, so you have to be a bit careful with this. But in general, it's not too sensitive unless you do something completely crazy. But yeah, it's a good point. On the other hand, of course, the short-range interactions are always are always locally calculated with the tree, anyways, which doesn't have any preferred directions. It's only the very large scales where this potentially can be a problem. Any other questions? Yeah.
So the third direction here, the T, you said some comments about that.
Yeah, it's essentially I projected through it. So I think I projected through it. Actually, let's check in the code. So you see this histogram call here. You can see what I did here. I read in the data, the positions and the masses, and then I make a histogram for the x-axis and the y-axis, which means that it projects all along the z-axis. So you could refine this if you want to have a slice, for example. You could put in here a statement that that calculates an index based on the z direction. Put this index in here and filter by the slice, and then give you just a slice histogram. But the problem with this simulation is you typically, since it's not an enormous amount of simulation particles, you cannot make a very thin slice, because then you just lack the statistics of the slice. Yeah. Any other questions? Yeah. Okay, good. If there are severe problems with installing the software, maybe we can chat tomorrow. Who has ever installed parallel C or parallel MPI environment or anything like that? So those of you who did this, it would be great if somebody gets stuck to maybe help, because that would be good. I mean, sometimes this can be a bit tricky, although these days the packages are pretty good and shouldn't be so difficult anymore. Also, I guess most of you have experience with installing